The granite columns are still there. Walk through certain districts of Paris, and you will notice them, thick stone pillars, sometimes integrated into building facades, sometimes standing alone in courtyards. They are typically 1 meter in diameter, and they run vertically through multiple stories. Most passers-by assume they are structural elements or ventilation shafts. They are neither. These are the remnants of a compressed air distribution system that powered factories, workshops, and machinery across Paris for over a century, a pneumatic grid that once rivaled electricity in its reach and sophistication. The Compagnie Parisienne de l'Air Comprimé began operations in 1881, and at its height, the system delivered compressed air through 186 kilometers of underground mains to thousands of subscribers. The infrastructure was not fully decommissioned until 1994, but the physical evidence, the columns, the valve housings, and the receiver tanks remains embedded in the city's architecture. It is a fossilized energy network that most people no longer recognize for what it is. The system was not experimental, it was profitable, commercial infrastructure that operated continuously for 113 years, outlasting many technologies that seemed more promising at their introduction. The fact that this history has become essentially invisible within a single generation reveals something fundamental about how technical knowledge persists or disappears, regardless of a technology's actual scale or success during its operational lifetime. The concept was not Parisian in origin. Compressed air as a power transmission medium emerged from mining operations in the ALPS during the 1850s. The Mont-Cenis tunnel project connecting France and Italy through 13 kilometers of solid rock required drilling technology beyond what muscle power or steam engines positioned inside the tunnel could provide. Engineers developed water-driven compressors on the surface that forced air through iron pipes to pneumatic drills deep underground. The system worked. Drilling rates increased 7-fold compared to manual methods, and the tunnel was completed in 1871. What began as a solution to a specific excavation problem revealed a broader principle. Compressed air could transmit power over distances and around corners in ways that mechanical shaft systems and even early electrical transmission could not match. The engineering challenges were substantial. They included maintaining pressure over kilometers of pipe, preventing condensation that would freeze tools in winter conditions, and designing valves that could withstand the constant cycling of high-pressure air. But these challenges were solved through iterative design improvements documented in the technical literature of the period. The Revue Universelle des Mines published detailed accounts of the compressor installations, including specifications for the Sommeiller-Colladon compressors that powered the drilling equipment. Water columns driving pistons with 600mm cylinders producing air at 7 atmospheres and capable of supplying 12 pneumatic drills simultaneously operating at depths up to 1,000 meters from the compressor station. Victor Popp saw the urban application. An engineer trained in Budapest and Vienna, Popp had worked on various pneumatic systems before arriving in Paris in the late 1870s. His insight was not technical innovation but infrastructural vision, recognizing that the same principles proven in alpine tunnels could serve urban workshops and factories. Paris in 1880 was a city of distributed small-scale manufacturing. The Haussmann renovations had created wide boulevards and modern sewers, but most production remained in small workshops scattered throughout residential districts. These operations needed mechanical power for lathes, presses, saws, and textile machinery, but could not efficiently install individual steam engines. A single steam boiler in a small workshop created fire risk, required constant attention, and operated inefficiently at small scale. Gas engines existed but were expensive, temperamental, and likewise posed explosion risks. Popp's proposal was straightforward: build central compressor stations, distribute compressed air through underground pipes like water or gas, meter consumption, and charge by volume. The Compagnie Parisienne de l'Air Comprimé received its operating concession in 1878 and began construction of its first station at Quai de la Râpée in 1880. It was strategically located along the Seine, where cooling water was abundant and coal delivery by river barge was economical. The technical specifications are not ambiguous. Patent records from the 1880s detail the system's design with precision. The main compressors at Quai de la Râpée were compound steam engines, each with a low-pressure cylinder 1,100 mm in diameter and a high-pressure cylinder 650 mm in diameter, driving air compressors with cylinders measuring 800 mm in diameter and a stroke of 1,200 mm. These machines operated at 60 revolutions per minute, producing approximately 32 cubic meters of free air per minute per unit, compressed to 6 bar. The distribution network used cast iron mains ranging from 50 mm to 500 mm in diameter, buried at depths between 1.5 and 3 meters below street level, following the sewers and utility corridors that Haussmann's renovation had established. Subscriber connections branched from these mains through smaller diameter pipes, terminating in the vertical columns that ran up building facades to individual workshops and factories. Each connection point included a pressure regulator and a volumetric meter. The company charged by the cubic meter of air consumed, measured at atmospheric pressure, with rates varying by time of day and subscriber class. Metering technology was sophisticated, with rotating vane meters and mechanical counters, sealed units that required breaking a lead seal for inspection, the same principle later adapted for natural gas distribution. The meters were manufactured by Elster, a German company that became a major supplier of utility metering equipment across Europe, and examples of these specific pneumatic meters survive in museum collections, including the Deutsches Museum in Munich and the Science Museum in London. The diversity of applications was remarkable. The Bon Marché department store used compressed air to power its freight elevators, large pneumatic cylinders, some over 1 meter in diameter, lifting platforms through multiple floors without the electrical infrastructure that would later become standard. The system was inherently safe for retail environments because air leaks created noise but not fire risk, a significant consideration in an era when electrical systems were still prone to arcing and insulation failures. Printing operations across the city used pneumatic motors to drive rotary presses, particularly for newspaper production where constant speed operation was essential for consistent ink distribution and paper feed. The Imprimerie Nationale, France's state printing house, had documented installations of pneumatic motors rated at 50 horsepower, connected directly to the city system and operating continuously during production runs. Clock synchronization extended beyond decorative timepieces. The pneumatic pulse system coordinated time displays at railway stations, government offices, and commercial buildings across Paris, all receiving minute, precise pulses from a master clock at the compressed air company headquarters. This was not primitive technology. The pulse distribution system required pressure-sensitive valves that could distinguish between regular synchronization pulses and pressure fluctuations from industrial loads elsewhere on the network. Engineers solved this problem through carefully calibrated regulator design, documented in contemporary engineering journals, specifically the Annales des Mines volumes from 1889 to 1892. The clock system alone represented significant sophistication. Over 8,000 pneumatic clocks operated in Paris by 1900, all synchronized to better than 1 second accuracy, creating a distributed time standard that preceded radio time signals by decades. If you appreciate research that prioritizes archival documentation over speculation, Content that builds arguments from verifiable evidence rather than sensational claims, consider supporting this channel. The approach here is straightforward. Identify technologies that existed, functioned, and left physical traces, then examine why they disappeared from collective memory despite their demonstrated capability. This is not about conspiracy or suppressed invention. It is about the economic, technical, and social factors that determine which technologies persist and which fade, even when they worked exactly as designed. Pneumatic power distribution represents a particularly clear case, a system that operated successfully for a century, whose infrastructure can still be located and examined, yet which has been almost entirely forgotten outside specialized engineering history. The documentation exists in accessible archives. The physical evidence remains visible in multiple cities. What disappeared was the living knowledge of people who understood these systems as everyday infrastructure rather than historical curiosities. Other cities replicated the model with local variations. Birmingham, England operated a compressed air system from 1890 onward, with a central plant in the jewellery quarter powering workshops that produced small metal components such as watch parts, decorative metalwork, and precision instruments. The system there used higher pressure than Paris, operating at 8 atmospheres, and it used smaller diameter distribution mains reflecting the denser urban layout and shorter transmission distances. The Birmingham system was particularly well documented because it served a concentrated industrial district where the economics were exceptionally favourable. Hundreds of small workshops within a few square kilometres, all requiring modest amounts of intermittent power. Exactly the application where distributed small engines were most inefficient and centralized power distribution most advantageous. The Birmingham Daily Post published detailed accounts of the system's installation in 1890, including cost comparisons showing that pneumatic power cost subscribers approximately 30% less than operating individual gas engines for equivalent work. Buenos Aires installed a compressed air network in 1896, primarily for industrial subscribers in the Port District, with compressors driven by imported British steam engines and a distribution system that extended roughly 30 kilometers at peak operation. The Buenos Aires system is particularly interesting because it operated in a climate with minimal freezing risk, eliminating one of the major technical challenges that plagued European systems: condensation management. Dresden's system, established in 1888, powered machinery in the city's textile mills and served the Hoftheater for stage machinery operation, with pneumatic winches and curtain mechanisms that provided reliable, controllable power for theatrical productions. Victor Popp himself consulted on several of these installations, and the technical journals from the period, including Engineering, The Engineer, and Zeitschrift de Verein Deutscher Ingenieure, contain detailed descriptions of these systems with diagrams, performance data, and operational cost comparisons with alternative power sources. These were not experimental demonstrations, they were commercial utilities with subscriber bases, published rate schedules, maintenance records, and documented operational histories spanning decades. The Offenbach system in Germany, established in 1891, served leatherworking factories and bookbinding operations, applications where electric motors were considered too risky due to the presence of flammable solvents and paper dust. The system there included a secondary network operating at reduced pressure, specifically for ventilation applications. Compressed air released through perforated pipes provided forced ventilation in workshops where natural airflow was insufficient. Mexico City established a limited compressed air system in 1900, primarily serving government printing operations and the National Mint, where the absence of spark risk was essential for operations involving explosive materials used in printing and metal processing. The technical literature documents at least 18 cities that operated commercial compressed air distribution systems from 1880 to 1920, with combined distribution networks exceeding 800 kilometers of underground mains. The thermodynamic inefficiency was understood from the beginning and never hidden. Compressing air generates heat, significant heat that represents wasted energy unless captured and used. The theoretical maximum efficiency for isothermal compression at 6 atmospheres is approximately 65%, but practical systems achieved far less. The Paris compressors operated closer to 40 to 45% conversion efficiency from steam power to compressed air energy, with additional losses in transmission through the pipe network, estimated at 5 to 10% depending on distance and flow rates. This meant that for every unit of coal burned to generate steam, only about 35 to 40% of the energy reached the subscriber's pneumatic motor. Early electrical systems of the same period operated at roughly 50 to 60% overall efficiency from coal to mechanical output at the point of use. The compressed air advocates didn't dispute these numbers. Their argument was that centralized compression allowed for more efficient use of fuel than distributed small steam engines or gas motors, that the infrastructure costs were lower than electrical distribution networks with no insulators, no copper conductors, and no transformer substations, and that the safety advantages in certain applications justified the efficiency penalty. For workshops handling flammable materials, for food processing operations where spark risk was unacceptable, and for applications requiring variable speed control in an era before practical electrical speed regulators, these arguments held weight. Contemporary cost analyses published in engineering journals showed that in 1895, compressed air cost subscribers approximately 2.5 francs per horsepower hour in Paris, compared to 3.5 francs for equivalent mechanical output from small individual steam engines, and roughly 2 francs for electrical power where available, competitive enough to sustain a viable business model. The pneumatic motors themselves were engineering achievements often overlooked in the focus on distribution infrastructure. These were not simple piston engines, but sophisticated rotary devices designed for smooth operation and variable speed control. The most common type used rotating vanes sliding in eccentric cylinders, similar in principle to later rotary vane compressors, but operated in reverse. Patents from the period show remarkable sophistication. They describe self-lubricating vane materials, pressure-balanced valve timing, and speed governors that maintained constant rotational velocity under varying loads. The French manufacturer Gans et Compagnie produced pneumatic motors ranging from fractional horsepower units for driving sewing machines and small tools up to 100 horsepower models for industrial machinery. These motors could be mounted directly to equipment without intervening belt drives. They could be started and stopped instantly without warm-up periods, and they provided smooth torque without the pulsation characteristic of single-cylinder steam engines. The speed control was achieved through simple throttle valves. By restricting the airflow, the motor slowed proportionally, a level of control that electrical motors could not match until the development of electronic variable frequency drives in the 1960s. Museum collections contain numerous examples of these motors, particularly the Musée des Arts et Métiers in Paris and the Powerhouse Museum in Sydney, which acquired several units from the compressed air system that briefly operated in that city during the 1890s. The decline was economic, not technical. Electrical power distribution improved dramatically between 1890 and 1920. Transformer technology matured, allowing high voltage transmission over long distances with manageable losses. Electric motor design advanced, particularly with the development of reliable DC motors for variable speed applications and the eventual dominance of AC induction motors for constant speed loads. By 1920, electrical systems could match compressed air's safety profile in most applications through improved insulation and circuit protection. More critically, Electricity could serve lighting loads as well as mechanical power. A unified system for both applications proved more economically attractive than maintaining separate pneumatic and electrical infrastructure. The Paris Compressed Air Company never claimed superior efficiency. Their value proposition was safety, controllability, and avoiding the capital cost of distributed boilers or generators. As those advantages eroded, subscriber numbers declined. The company converted some of its distribution capacity to carry compressed air for pneumatic message tube systems, the pneumatic post network that moved small containers of documents through pipe networks in Paris and other major cities, but this represented a fraction of former industrial demand. By 1960, the subscriber base had contracted to a few hundred specialized users. The transition was not abrupt. The 1930s saw relatively stable subscriber numbers, and the system actually gained some users during World War II when electrical supply became unreliable. But the long-term trend was unmistakable, and by 1970, the remaining subscribers were primarily legacy users, with equipment too expensive to replace or specialized applications where compressed air retained specific advantages. The system lingered through inertia and the longevity of its infrastructure, finally shutting down in 1994 when the remaining contracts expired and maintenance costs for the aging pipe network exceeded revenue. The final subscribers included several watch repair workshops in the Marais district, a small bindery near the Bastille, and remarkably, the pneumatic clock system which continued operating until 1927, outlasting most industrial users by decades. The compressor station at Quai de la Rapée was demolished in 1998 to make way for riverside development, but photographs and architectural drawings preserved at the Archives de Paris document its layout in detail. A four-story building with ground-floor compressor halls, upper-floor offices, and a distinctive cylindrical tower that housed the master clock for the pneumatic time distribution system. The site now houses modern apartments with no indication of its former purpose, though the river wall retains enlarged sections that once accommodated the intake pipes for compressor cooling water. The physical infrastructure outlasted the service because removal cost more than abandonment. The underground cast iron mains were buried beneath streets, sidewalks, and building foundations. Excavating them would require tearing up roadways, coordinating with other utilities, and disposing of thousands of tons of iron pipe. The simplest solution was to cap the system, drain any remaining condensate, and leave it in place. The vertical columns posed a different problem. They were integrated into building structures, often passing through multiple floors, sometimes load-bearing or at least presumed to be load-bearing by subsequent building owners who had no records of their original purpose. Removing them would require structural analysis and potentially costly remediation. Most were simply left in place, sometimes cut off at ground level and capped, sometimes retained and repurposed as ventilation shafts, or simply as unexplained architectural features. You can identify them by their distinctive characteristics: unusually thick granite or cast iron columns, often positioned in building corners or against exterior walls, typically showing evidence of heavy-duty pipe fittings at their base, sometimes retaining fragments of brass valves or pressure gauges. The 9th arrondissement, particularly around Rue Lafayette and Boulevard Haussmann, has numerous examples. The 11th arrondissement, historically heavy with small manufacturing workshops, retains even more. The building at 45 Rue de Turbigo shows a particularly clear example: a granite column approximately 1.2 meters in diameter, running from basement to 4th floor, with visible valve mounting brackets at ground level and a capped pipe terminus in the basement that once connected to the distribution main beneath the street. These are not hidden or destroyed, they are simply no longer recognized for what they are. The knowledge loss occurred within a single generation. Engineers who designed and maintained the pneumatic systems retired or died between 1950 and 1980. The The technical literature documenting these systems remained available in specialized libraries, the Conservatoire National des Arts et Métiers in Paris, the Science Museum Library in London, and university engineering collections, but it ceased to be referenced in current engineering education. Compressed air remained in use for specific applications, pneumatic tools in workshops, air brakes on trains and trucks, and control systems in process industries. But the idea of compressed air as a general power distribution medium, as urban infrastructure analogous to electricity or water, disappeared from engineering discourse. By 1990, most practicing engineers under the age of 50 had never encountered the concept, except perhaps as a historical footnote in textbooks about the development of electric power. The physical evidence remained visible, but the interpretive framework to understand it had vanished from common knowledge. This was not conspiracy or suppression. It was simple obsolescence combined with the normal turnover of technical expertise. Technologies that stopped being used, stopped being taught, and within decades, even recent history becomes obscure. Textbooks document the transition. Textbooks from 1920 discuss compressed air distribution as current technology. Texts from 1950 mention it as recently obsolete. Texts from 1980 onward typically omit it entirely except in specialized historical surveys. Pneumatic message systems suffered a similar fate, but they left more obvious traces. Pneumatic post tubes operated in major cities across Europe and North America from the 1860s through the 1950s, moving small containers through pressurized pipe networks at speeds reaching 50 kilometers per hour. Paris had the most extensive system with over 450 kilometers of tubes connecting post offices, government ministries, newspaper offices, and the stock exchange. The tubes were typically 65 millimeters in diameter, running in separate networks from the power distribution system and using lower pressures, about 0.5 atmospheres, with direction controlled by valves at junction points. The physical installation was similar to the power mains, underground conduits following street layouts, vertical risers in buildings and terminal stations with pressure gauges and dispatch controls. New York system operated from 1897 to 1953, covering Manhattan with tubes that connected 23 post office stations, handling an estimated 95,000 messages daily at peak operation in the 1920s. That New York system was particularly well engineered, with automatic sorting junctions that routed containers based on address codes stamped on their exterior, essentially mechanical packet switching decades before computer networks. London's system served the financial district and government offices with heavy usage connecting the stock exchange, the Bank of England, and major commodity exchanges where rapid information transmission provided competitive advantage. Berlin's network connected military installations and government ministries, and portions of that system remained operational until 1976, serving East German government offices. Prague's system continued operating until 2002, one of the last survivors of what had once been standard urban infrastructure, finally closing when maintenance costs for the aging tube network became prohibitive and electronic communication eliminated any operational advantage. When these systems closed, the tubes were typically abandoned in place for the same reasons as the power distribution mains. Excavation cost exceeded salvage value. Building demolitions occasionally expose sections of brass tube junction valves and pneumatic cylinder mechanisms from dispatch stations. Most people who encounter these artifacts have no reference framework to identify them. The Museum of London has a preserved section of pneumatic post tube excavated during Crossrail construction in 2015, complete with junction valve and direction indicators, displayed with minimal explanation because curators assumed viewers would recognize what they were looking at. That was a reasonable assumption for objects that were operational urban infrastructure within living memory. Yet, visitor surveys showed that less than 15% of museum visitors could identify the display's purpose without reading the accompanying text. Similar discoveries occur in other cities during utility work or building renovation. Sections of tube network, dispatch station equipment, and compressed air infrastructure are often interpreted as generic pipe systems or simply discarded as unidentifiable debris. The lesson is not about lost superior technology. Pneumatic power distribution was not superior to electricity by most metrics. The lesson is about the contingency of technological memory. We assume that important technologies remain known, that significant infrastructure leaves lasting recognition, that recent history is adequately documented. The reality is that operating knowledge is fragile. Documentation exists, but it requires active effort to maintain accessibility and interpretation. The Paris compressed air system had thousands of subscribers in 1900, employed hundreds of workers, required significant capital investment, and operated successfully for a century. Within 30 years of its closure, most residents of Paris had no awareness it ever existed. The physical evidence remains. You can walk to specific addresses and photograph the granite columns. You can consult archived maintenance records at the Archives de Paris. You can examine pneumatic motors in museum collections at the Musée des Arts et Métiers. None of this prevents the technology from becoming functionally invisible to contemporary awareness. This pattern repeats across industrial history. Systems that worked, that served real needs, that left substantial physical traces, can become obscure simply through the normal process of technological replacement and generational turnover. The compressed air columns in Paris are not mysterious or controversial. They are just forgotten, preserved in plain sight, waiting for anyone curious enough to investigate what those unusually thick stone pillars actually represent.